Have you ever stopped to think about what really happens when you run a program on your computer? I mean, we type these commands that kind of look like English, but our machines, they only get one thing: electricity, ones and zeros. So, how do they understand us? Well, today, we're going to pull back the curtain on one of the most fundamental, most fascinating processes in all of computing, that incredible journey from a human idea into a machine's action. Okay, let's just start with the core problem right here. Look at this. On the left, you've got a command that's readable for a human, right? Add 5. A programmer gets that instantly. But on the right, that's the computer's native language. It's just a raw stream of on and off signals. The gap between these two is absolutely massive. Trying to bridge it is like, I don't know, translating a beautiful poem into Morse code. The entire structure of the language has to fundamentally change. And this gap, this communication problem, is what we call the language barrier. Honestly, it is the central challenge that the pioneers of computer science had to solve. If they hadn't found a way to cross this barrier, computers would have just been these super complicated calculators, totally inaccessible to pretty much everyone. So yeah, that is the big question, isn't it? How in the world do we get from a simple, clean instruction like add to this long, complex string of ones and zeros that a tiny silicon chip can actually execute? Well, the answer lies in a set of incredibly clever, absolutely essential programs. And that brings us to the world of system programming. I want you to think of this as this specialized toolbox that developers built specifically to solve this translation problem. These aren't the apps you use every day, like your web browser or a game. Nope. These are the powerful tools that make all those other apps possible in the first place. At their core, system programs are the unsung heroes, working away in the background. They're the ones handling all the messy, complicated details of the hardware, so that application programmers and, by extension, all of us, don't have to. They're basically the ultimate support staff for our entire digital world. And inside this toolbox, we have our core translation team. It's kind of like a little assembly line. For this explainer, we're really going to zoom in on that first worker, the assembler, but it's super important to know that it works with its teammates, the compiler and the loader. Each one has a very specific job to do to get our code down the line. The assembler is our star player today. It performs the most direct translation you can possibly do. It takes a very low-level symbolic language called assembly and converts it, almost one for one, into that binary machine code we saw a minute ago. Now, a compiler, it works a little differently. It works with higher-level languages, things you've probably heard of, like Python or C++. It takes code that's more abstract and human-friendly and does a much more complex translation, often having to break a single human command into many, many machine instructions. And finally, we have the loader. So once the assembler or the compiler has done its job and created that binary code, the loader has one last crucial task. It grabs that code from your hard drive and places it into the computer's main memory, the RAM, so the processor can actually get to it and run it. It's the final handoff. So how does an assembler actually work its magic? It's really cool. It doesn't just translate everything in one single shot. Instead, it uses this clever two-step or two-pass process. And that first step, pass 1, is all about getting prepared. This quote nails it. Imagine you're a translator, and you've been given a super technical manual to translate. Before you even start writing sentences, what would you do? You'd probably go through the whole thing and create a glossary, right? A list of all the special terms and what they mean. Well, the assembler does the exact same thing with your code. As you can see in this flowchart, pass 1 is basically a scanning phase. The assembler reads through the entire program, but listen to this. It's not generating any machine code yet. Its only job is to follow the program's logic and find all the labels and symbols, basically any custom names the programmer made up, and to build a map of exactly where they are. And this is the brilliant result of pass 1. It's called a symbol table, and it is that custom-made glossary for our program. It's a simple list of every symbol the programmer defined and the exact memory address where that thing lives. This table is the absolute key to the entire process. All right, now for pass 2. With our glossary, that symbol table, all filled out and ready, the assembler is ready for the main event. It literally rewinds to the beginning of the program and starts reading through it a second time. And this time, it's actually translating. So, for every single line of assembly code, the assembler now knows exactly what to do. It looks up the instruction itself, like add, in its own built-in dictionary. And for any of those custom symbols or variables, it just looks them up in the symbol table it just created during Pass 1 to find their memory addresses. Simple as that. What's so cool about this flowchart is you can really see the logic in action here. The assembler reads an instruction, it breaks it into its different parts, it looks up the values for those parts using that symbol table it just built, and then it just methodically puts together the final bits and bytes of the machine instruction. It's a really careful step-by-step construction process. And at the end of Pass 2, we have it, our final product, the object program. This is a file that contains nothing but pure, unadulterated machine language. It's the raw binary code that the loader can now hand directly to the CPU to execute. The translation is finally complete. Okay, so after seeing that whole complex two-pass process, you might be asking yourself, why on earth would anyone choose to write an assembly language, right? With all these powerful modern languages out there, why would you operate at such a low level? Well, it all comes down to a classic trade-off. The power of assembly is all about direct control. It gives you faster translation times and lets you write incredibly efficient code that is perfectly tailored to one specific processor. But the price you pay is steep. Your code is not portable. It will only run on that one type of computer, and you need to have deep, expert knowledge of the hardware. Plus, even simple little tasks can take many, many lines of code to write. So let's zoom out one last time and put our assembler back in context. How does its direct two-pass translation method really stack up against the other tools in the system programming toolbox? So we've already met the compiler, which, a lot like an assembler, translates the entire program all at once before you run it. This generally makes the final program run very, very fast. An interpreter, on the other hand, is different. It translates and runs your code one line at a time. This is usually slower, but it can make finding errors, what we call debugging, a whole lot easier. And hey, as a quick bonus, let's just touch on two related ideas from the world of operating systems. Multiprocessing is when you use multiple CPUs, multiple brains, to run tasks in true parallel at the exact same time. Multiprogramming, on the other hand, is a really clever trick for a single CPU to juggle multiple programs, creating the illusion that it's doing many things at once. Both are all about squeezing every last drop of efficiency out of the hardware. And you know, that brings us to our final thought. We have built layer after layer of abstraction on top of the bare metal of the machine. But no matter how advanced, how smart our languages become, somewhere deep, deep down, a program very much like the assembler we just explored is still doing the essential foundational work of bridging that gap, of translating our big ideas into the only language the machine will ever understand. So what do you think the next evolution of that translator is going to look like?